All right, folks, today we're going to start talking about rotations. Rotations can be measured in a few different things, some of which you recognize and one of which that is new. Okay, so we've got degrees. That's something that you already know about. That's the most common way to measure a rotation. Okay, but also we can deal with radians. That's new. You've seen the word before, but haven't really known what it meant. And then revolutions, which really just means another name for lap. Okay, once we have an idea of these things, then we're going to talk a little bit about sectors as well. Okay, so make sure you have a calculator. You're going to need it for some of these conversions we're doing, and we'll get started. So the big idea is when we're talking about some sort of rotation, we usually deal with measuring that rotation from some starting point, and we're going to reference our starting points on a circle. Okay, so imagining this circle, we're going to let the radius of this circle be 1, and it has a special name when we do that. It's called the unit circle, meaning the radius is 1 unit long. Okay, then we have our center of the circle at a point, and a lot of times when we fixate this circle on a coordinate system, that point itself, the center, is at 0, 0, and we'll focus more on that next time. Okay, for now, we're going to talk about the relationship between these three items, the degrees, radians, and revolutions. We already know if we're thinking about a circle, that's 360 degrees. When we're talking about that as a rotation, it would be this radius rotating all the way around the circle, meaning 360 degrees was the measure of that. Well, that's also known as 1 revolution. Okay, we think of it as 1 rotation, but it's 1 revolution. Okay, the new part today is dealing with radians, and that's going to come from something that you already know as well. Okay, we're going to talk about some formulas that we know about circles. Okay, one of them is circumference, or the distance around this circle. Well, we're talking about around this circle in terms of our rotation, so the circumference is going to be helpful for us. The formula is 2 pi times r, where r is the radius, and if we know our radius is 1, that looks like 2 pi times 1, which means our distance around is 2 pi units. We're going to call that our radian measure. So you'll notice this doesn't have a label attached to it like these other two. When you don't see a label, that is our radian measure. So now when you've seen in trigonometry, when you took it in geometry, that mode mattered. We had to switch our mode from radians to degrees. We're going to be interchanging back and forth between both of these because this radian measure is actually very helpful in terms of trigonometry. So we're going to start just practicing getting used to moving from one version to another, some conversions, jumping from degrees to radians to revolutions and back. Okay, so on each of these problems, it tells you what you start with, and it tells you what you want to end with. We're going to set these up instead of as a proportion, just as a way to multiply by a factor to get to what we need to. So here's how it's going to work. We're starting out with 60 degrees on this first one, and we want to end with radians. That formula or that statement at the beginning is going to be very helpful for us to do this. Here's what I want you to start with. Whatever number you're given goes first, and that's just going to go by itself. And what we're going to do is multiply it by a fraction, or our factor, to eliminate what we have and to get what we need. So remember, we've got 1 revolution is the same as 360 degrees is the same thing as 2 pi radians. We're going to pick the two of these that are involved in our conversion. So this one has degrees and radians, which means we got to focus on those two pieces in this statement. And what we always want to do to have things cancel out is whatever we have on our first part needs to be in the denominator of this fraction. So the degrees portion, the 360, has to go on the bottom to cancel out our label of degrees. Then on top is whatever we need. So we need radians, that 2 pi will go on top. So then, this is where your calculator comes into play. You don't have to reduce this by hand necessarily. You can pretty easily on this one, but in general, you can throw this whole thing in your calculator except for the pi. Okay, so what I mean by it's usually easy to reduce by hand is we can cut off those zeros easily. 6 over 36 is just 1/6, and then 2 over 6 is 1/3. and then that pi goes to the side. Okay, but it's just as easy sometimes to throw it in our calculator. 60 times 2 divided by 360. And your calculator can change that to a fraction we know for us as well. A lot of times fractions are going to be nicer for us, but there's nothing wrong with writing these as decimals in a case where it ended up looking nicer than the fraction. Okay, so this one, 1/3 pi, you could have also left it as that 0.3 as long as you use repeating. We just have to make sure that we throw that pi on the end, and that's our radian value. With radians, just like in the original statement, you don't need a label. It's implied. A lot of these are going to have pi in your answer. They don't necessarily have to, though. In some weird instances, we do see those pi's cancel out. Okay, don't leave it off, though, in your final answer if it definitely started out that way. All right, let's look at the next one. Again, we're starting the same way. We're going to always write down what we're given and make a fraction next to it. And we're always going to match what we see to go in the denominator. So we see degrees, we're putting that 360 again on the bottom, but this time we're trying to get to revolutions. In this statement, it just says the number 1 revolution, so that's what's going up top, which means we just have to take this 450 divided by 360. We don't really have to times it by 1. Okay, for this one, again, I think it's easier to reduce by hand, but you're welcome to just throw it in your calculator as well. 45 and 36, you can take a 9 out of both of them, so it's 5/4 revolutions. If you did it in your calculator, that would have looked like 1.25. I will take either one as long as there's a label attached to it. All right, next up, this is the first time we see pi to start with. Okay, 7.5 pi, we write that whole thing down. And then we're going to match over here the piece that has pi in it as well. But remember, these don't always have to show up. They just most times show up. Okay, so without a label, it is radians. We've got radians here. We're putting radians in the denominator, so our 2 pi goes there. And we're trying to get to revolutions, so 1 revolution goes up top. Okay, always cancel your pi's if you see them. Okay, if you don't see it, like over here, we just leave it out and tack it on the end. Okay, so here, those actually canceled, and we just have to take 7.5 and divide it by 2. That's 3.75, and putting our label on the end. All right, let's take a look at these next ones. We're just practicing with these to get more familiar with switching forms here. This negative that you see represents we are going clockwise instead of counterclockwise. Okay, we learned in geometry when we're talking about rotations, okay, when we're measuring with a protractor, we always went backwards. So counterclockwise is actually standard. And then if you see the negative, it means it goes the other direction. It goes clockwise. So we're going negative 44 degrees, or 44 degrees clockwise, and we're going to change that to a radian measure. So again, degrees on top, so we're putting 360 on the bottom, and we're finding the piece from that original statement that goes with radians, and that is 2 pi. Okay, that is something you're going to have to know, that 2 pi is the same thing as 360 degrees, is the same as 1 revolution. Okay, but it's only got 3 pieces, and one of them you already know. All right, from there we're just throwing this thing in our calculator because it's not as easy to reduce as the last ones. Again, if pi's don't cancel, you're going to leave it out when you type it in. Okay, so you're doing your negative on there, 44, times 2 divided by your 360. Your calculator's smart enough to figure that out. Okay, this one's not the best decimal. We've got a repeating decimal place, but it's not until the second one. Okay, a lot of times I like to hit math enter, see if it's better. In this case, they're about the same. You get to choose. Okay, so I will take either of those. Just make sure you put the pi to the side. Okay, and that's your final answer. Now, I do want to point out there are 2 ways that you can write your final answer in this case, not just decimals or fractions. With this negative involved, you could say it's negative 11/45 pi, or you could say 11/45 pi. Okay, that's a radians, but it's going clockwise. Okay, so you could just say clockwise instead. Now, why that's important to recognize is sometimes instead of this negative, they will just say clockwise, and you have to make sure that either stays on there or you're tacking a negative on to your answer. All right, we'll do a couple more together here before I set you loose to try some on your own. Okay, we've got a negative again on this one. We're just changing this one to revolutions, starting out with what we're given and multiplying by our fraction. We're putting 360 degrees on the bottom to get rid of those degrees, and we're putting 1 revolution on top. This one we're just multiplying straight across, but this one doesn't matter, so we just have to divide those two. Okay, when we divide those two, we've got a negative happening, and it's negative 0.625. Okay, because I'm guessing put that one in your calculator, but this one is also a decent fraction. Either one will work for me, again, as long as we put revolutions to the side. Okay, if it's starting negative, I'll usually write negative. Okay, but revolutions is talking more about our rotation, so a lot of times this one, out of any, you won't see this, you'll see clockwise. Okay, you will see this, I will take either. Okay, you can put the negative or write clockwise, I don't care what you write. Alright, next up, we've got a negative 9 over 2 pi, that is our radian measure, and we want to change it to revolutions. Negative 9 halves, multiplying, we know we're seeing this pi, it's in radians, we're putting radians on the bottom, and then we've got revolutions on top. Okay, don't be scared by these fractions, we want to cancel out our pi just like normal. Okay, and when we're thinking about this fraction, since it's got one over here to start with, we just want to think about multiplying straight across. This is negative 9 on the top and 4 on the bottom. There's no reducing necessary here. We tack on our revolutions and we're done. Okay, if you throw this in your calculator, you do have to be careful. Let me show you why. If I just type this in, negative 9 over 2, and then I divide it by 2 again, because that's what's next over here, your calculator on this one does all right. But sometimes this part right here actually does this piece in the wrong order. And because of that, you really want to be careful. The only way to fix this to make sure your calculator does it right all of the time, if you want to use that, is change these to 2 separate fractions and include that 1. So instead of going like I was showing you that first time, you would have to go negative 9 divided by 2 times the 1 divided by 2, and that'll save you from the fraction within a fraction sometimes coming out wrong. This was a special case that didn't come out wrong because of that 2 divided by 2, so do be careful, please. Alright, I'm going to have you pause the video at this point and try 7 through 12 on your own. Okay, I will show you the answers here when you're done, okay, but I want you to pause the video and try them first. Alright, I'll let you check your answers for these 3, 7, 8, and 9. Showed my work there. And then I'm going to have you take a look at your number 7 again, and I want to show you something special about problems like 7, 10, and 11, okay? Or 7 and 10. When you're dealing with radians that include pi, there's a shortcut that we need to get familiar with. We know that 360 degrees is the same thing as 2 pi because when we think about a circle, all the way around we decided was 2 pi. But when we're talking about circles, it's often helpful to think about not only a full circle, but a semicircle. And if all the way around is 2 pi, then half the way around is, we know, 180 degrees, but that's the same thing as pi. To show you algebraically here, we can divide by 2 on both sides, and pi is the same thing as 180. We want to get familiar with this, because if we know pi is 180 degrees, then when we're changing from radians to degrees, the easiest way to do so is with substitution. we can substitute pi with 180 and simplify a little bit faster, because 180 divided by 3 is 60, and 60 times 2 is 120, and it's done. Okay, the same thing can be done on number 10. I'll let you take a minute to check your answers 10, 11, and 12. Okay, but when we see this pi and we're changing it to degrees, again, we can do so with substitution. Okay, when we multiply negative 12 over 5 times 180, again, we could simplify it the same way. 180 divided by 5 is 36 times 12. It gives us that answer faster than having to worry about canceling these and reducing. Okay, so 360 is the same as 2 pi. 180 is the same as 1 pi, and we can use substitution. Okay, we'll practice that more next time. It's going to be very, very useful, but that's something I wanted to show you just as a preview. The next thing we're going to talk about is sectors. A sector is just a fancy way to say a piece of a circle. Okay, and a piece of a circle marked off by a central angle. Okay, so it has to have this point at the center. So what we're going to do is talk about both the area of sectors and the arc length of a sector, and those relate to the formulas that we already know. So area of a circle is pi r squared. Circumference all the way around is 2 pi r. Already talked about that one. Okay, but what we want to do is be able to find the area of this portion of the full circle, or this curve of the circle, not all the way around. Okay, the easiest way to show you how to do that is dealing with a really basic piece. Okay, so I've shaded a portion of the circle, and it's really easy to see that this portion of the circle is a quarter. Okay, what we can do is find the area of the whole circle and then just divide it by 4, or multiply it by this 1/4. But this piece is really important for us. Okay, where it comes from is this shaded portion. The central angle here forms a right angle, so that's really 90 degrees out of 360 degrees. That's our 1/4. Okay, very similarly, and this is new, we could call it, instead of 90 degrees, that's the same thing as pi over 2 radians, and that's not something that I would need you to know automatically. Okay, but I do want to show you that it's equivalent if we have 2 pi on the bottom instead of 360. That's our full circle. Pi over 2, this fraction is also 1/4. Let me show you why. Okay, this pi over 2 I'm going to leave alone. And I'm going to multiply by this thing is in the denominator, so it's like 1 over 2 pi. Then those pi's cancel out, and we can see the 1 is on top, 2 times 2, 4 is on the bottom. Now why this relates and why this is so important is because our formula for our area or circumference of just a sector, all we have to do is take that central angle in the corner and put it over either 360 degrees or 2 pi, depending on whatever our angle is given to us as. This pi over 2 you didn't have to know, because we're going to be given that piece of information. We'll be given that central angle if we're asked to find the area or the circumference. Okay, so let's test it out for this first example. And this first example, they give us this central angle in our picture and up here in radians, which means when we're using our formula, we want to times by the angle theta over 2 pi rather than over 360, just because that was given to us that way. Okay? Here's how it works. What we want to do is come up with our formula in the simplest way first, and then substitute in numbers. Okay, so if we're asked for the area, the first thing I want you to do is write down our area formula of a regular circle. So that is pi r squared. Then beside it, I want you to multiply by theta divided by whatever you need, either 360 or 2 pi. We decided that this one was 2 pi. Okay, but before we plug in numbers, we are going to simplify this formula. The pi's will cancel because one's on top and one's on bottom. And then what we're going to do is actually move this 2 to the front. Okay, I want all coefficients in the front like we're used to seeing. Instead of to the side, we want our numbers at the beginning and our variables at the end. So we're starting with A equals, because this 2 is at the bottom, this is really 1/2, and then we write the rest. So this first is r squared, and next we're timesing it by theta, so it's just smushed. And there's our formula for the sector. Now that we have that, we can substitute in the information. From our picture, the radius is 5, so we're saying our 1/2 times 5 squared. And then the theta, also in the picture, was given to us as the 7/12 pi. Okay, the pi's canceled out here, and then the pi was part of our angle radian. That's why it's so important that we reduce ahead of time, so we don't have too many pi's in the picture. We don't know what cancels or doesn't cancel. All right, with this in mind, we're going to simplify. Again, you can throw this whole thing in your calculator if you want, or do some simplifying in your head. We've got 5 squared gets multiplied by this 7. Okay, so we've got 25 times 7. Okay, and then we're going to write that number on the top. And then our 2 times 12, that number goes on the bottom. They don't reduce. Pi goes to the side. Okay, that is our area because it doesn't reduce. And again, if you're throwing it in your calculator, you're welcome to put this as a decimal. It does not matter to me. Okay, but we want to think about our area as something squared. They gave us our label was just units, or when we're not given a unit, we throw that on so we can show that it's actually squared. Next thing we're going to do is the exact length, and that's dealing with our circumference. Again, we're starting with the formula we know and love, 2 pi r, and then we're multiplying by, again, theta over 2 pi because our angle was in radians. Again, before we put numbers in, we're going to reduce. 2 pi's cancel, which means our formula is super nice here. Our circumference piece is just r times theta. They're smushed. We were given both of those things, so we can say 5 times our 7/12 pi, and then multiply straight across. 5 times 7 goes on top, and the 12 goes on the bottom. Nothing reduces, so that's our answer with the little units to the side. This is just the length or piece of the circumference around, so we don't need a squared on this part. Alright, let's check out another one like that. This time we are given a central angle of 75 degrees. It doesn't give us a picture, but it gives us all the information, so we really don't need a picture. Okay, but because of this degrees, we're going to use theta over 360. That's always what you want to look for first, is the central angle. Let's make a note of that so we don't forget. Find central angle label, because that's going to tell us what to tack on the end. Alright, let's read the problem. It says find the exact length. Okay, so this is a circumference, 2 pi r to start with, and we're multiplying by theta over 360. That's what we decided. Again, we are always going to simplify the formula first. We don't have any pi's cancel out like this time, but we can reduce our 2 over 360 there. So C equals, this really is 180 here, but it's on the denominator, so 1 over 180, and then pi r theta. There's our formula, and then we're going to plug in our numbers. So I'm going to go over to the side here, 1 over 180. They gave us our radius was 6, so I'm plugging that in, and our theta was 75, so we're plugging that in as well. And then this whole thing can be typed into your calculator. Okay, we want to always leave the pi out so it's left exact. So 1 divided by 180 times 6 times 75. And it came out to a decent 2.5. So this is 2.5, don't forget the pi, with our label. And our label up here was given to us as feet. No squared because it was a length. Okay. Toughest part here is to remember that our pi, if we're leaving it out in our calculator, still has to go on our answer at the very end. Okay, next one is area. Okay, area is pi r squared. Again, it's a sector, so we're tacking on this piece. Okay, I want you to pause the video and try this one out for me, please. Alright, nothing here reduces, so you can put this 360 in the beginning, but because nothing's simplifying, you can actually leave it there. It's really up to you. So if you did it like the other problems and moved it here, that's great. And then we're plugging in numbers. The R was 6, and the theta was the 75 again, and your final answer should have been 7.5 pi with feet squared, since it was area. Okay. Next couple problems we're going to go backwards on. Okay, so it's still dealing with sectors, but we're solving for a different piece instead. It says a sector with central angle 2/3 pi, okay, has an area of this. So area is already given to us, but it is still important that the first thing we think about is what formula we need to use. Okay, so this one says area, so I'm going to start out with that. The second part, just like we talked about before, is we need to know if the central angle is in radians or degrees, so we know what to tack on the side. Okay, so it says the central angle is this. That looks like a radian measure, so we're going to tack on theta over 2 pi to the side. And just like the previous problems, we want to simplify before we substitute in. Okay, so the pi's are going away here, and this 2 is going in the front. So 1/2 r squared theta. Remember, it's 1/2 because that 2 is in the denominator, just a reminder. Okay, from there, we substitute in, but we're going to have to solve instead of just simplify, because this area was given to us. So we're starting out with 25 over 3 pi, and we're setting it equal to 1/2. Then our r is what we're solving for. We're leaving it r. And we're multiplying it by that theta, which was 2 pi over 3. Okay, so here's what I want you to do first with these. Just like we were talking about with the regular formula, we want our numbers together in the front, so we're going to multiply straight across to get those put together. So the 25 over 3 pi stays here, and over here I've got 2 over 6, or those 2's cancel, it's 1/3. R, and then the pi to the side. Okay, remember, if you see something on both sides of the equal sign, you got to just cancel them out. Okay, other way to put that, just let me show you here for a minute. We divide by pi on both sides to get r by itself here. Pen's loading here. And then those end up canceling out on both sides. Okay, so those are gone. And then we're stuck with 1/3 r equals 25 over 3. Well, the same thing actually applies to this piece. We see that 3 in the denominator on the same side. They actually go away. But let's talk about why. If this is 1/3 r, we can multiply by 3 to get rid of it. So I'm going to do that on both sides. Those cancel, leaving us just with r here. And on this side, those 3's cancel, leaving us with 25. Okay, I lost my squared in the process here somewhere. Okay, but that's r squared equals 25, which means my radius is 5. There's no negative for radius, so this one is just the positive version with a feet next to it. Okay, that same concept is going to be applied to number 18. It says the arc has a radius of 5 and a length of 25 over 8 pi feet. Find the measure of the central angle in radians and degrees exactly, so we have to solve for both versions. We want to find the formula first. So because it says length, this is a circumference problem. C equals 2 pi r. Next thing we're going to do is decide if this is theta over 360 or theta over 2 pi. Okay? Because central angle is what we're solving for, we can use either. Now, I know you're more comfortable with degrees, but I'm telling you, if you see 2 pi r here, you want to use 2 pi. We want to use radians because then our formula simplifies and makes this problem a whole lot easier. Okay, so look at what you're dealing with before you automatically jump to 360 there. Okay, it will come out the same either way, so it wouldn't be wrong to use 360. All right, let's look at this. C equals r theta. We're going to substitute in what we know. We know that the radius was 5, so that's going there. And we know the length, or the circumference piece here, is our 25 over 8 pi. Okay, and then theta to the side. Theta is what we're solving for here. To do this, we want to be careful. I know that dividing by 5 is how we normally get rid of this, but we don't ever want to see a fraction in a fraction, so that's not a good idea. Okay, look ahead, and instead of dividing by 5, let's go ahead and multiply by the reciprocal to eliminate that piece. That helps us on this side here. Okay, so we're left with theta, and on this side, 25 divided by 5 is 5. So we've got 5 over 8 pi. There's nothing wrong with you throwing this piece in your calculator if you do struggle with fractions. Okay, just make sure that pi gets on the end. So there is our angle in radians, and we're going to just change that to degrees. Okay, remember, you can set this up like we did it on the front page. Okay, when we're trying to get rid of radians, you put 2 pi on the bottom. If you're trying to get 2 degrees, that would put 360 on the top. Okay, but remember the shortcut I showed you. Pi is the same thing as 180 degrees. So if you know that that is 180 degrees, you just take 5 divided by 8 times 180, and you can get there a little bit faster. Okay, same answer if you use this formula or that shortcut. But we're going to get theta is also 112.5 degrees. These are your answers because it asked for both. Last thing we're going to do is talk about sectors, dealing with some word problems here. Okay, in order to do that, we need to talk about some vocab here. This vocab that we see is actually dealing with symbols, and these symbols are familiar, but they're used in a different way than you've seen them before. So we've got 55 degrees here. We're familiar with that symbol. This symbol we've seen before too, but we thought of that symbol as feet and 2 tick marks as inches. When we're dealing with rotations, it has a different meaning, so I need you to take some notes here. When we see a 1 tick mark, that actually means minutes for us, and I'll explain what it deals with here in a second. When we see the 2 tick marks, it's not inches for this, it is seconds. Okay, because a lot of times when we're talking about rotations, we're dealing with the circle. Well, also dealing with the circle is time, and what we're going to do is talk about breaking it up. We know 1 degree is a small unit, but we can also break this into even smaller units, and that's what these things represent. If we split 1 degree, and I'm going to blow this thing way up so we can kind of see what I mean here. So let me get rid of this. Imagine taking 1 degree and blowing it up. I know that's bigger than 1 degree. If I were to split this into 60 different pieces, that tiny little piece would be considered a minute. If I took this tiny little sliver and split it up again into 60 more pieces, that would be a second. Okay, so it lets us get really super accurate. And why that matters is because a lot of times these degrees are used to talk about navigation. So when we're talking about giving directions in terms of longitude and latitude, we want to be super accurate to get to our destination properly. So they split it up to the most accurate thing possible, and that's minutes and seconds, not just degrees. So decimal degrees have to happen from changing this notation into decimals. Okay, that lets us mathematically work with these pieces better. All we have to do is read it and then know what the pieces represent. If we see 1 tick mark, it's minutes. If we want to change that to a decimal, well, minutes, if we're taking that minute and splitting it back to the degree, we know that there are 60 of those pieces in a whole degree, like I just showed you. Okay, so here's how it works. In your calculator, you're going to put this whole thing in there. 55 is the whole part, so 55 plus. And then we're taking 32 divided by 60, and that'll give us our decimal degree. Okay, and we have to write it exactly. So this is 3 repeating, 55.53 with the bar as a degree. Same thing with the second piece. This again is a minute, so we're putting it over 60. Okay, and then typing the whole thing in. The whole part goes first, plus 44 divided by 60. And this one's 87.73 repeating with the degrees. Okay, I'm going to have you change this last one so you can see with seconds as well. So keep the part you see, but we're going to tack on one more piece. Let's do 54 with 2 dashes next to it. And this is our whole coordinate. If we see something like that, we're going to split it up into 3 pieces. The 13 is the whole, plus that 14 is the minutes, so that's over 60. And then we're adding it to 54, and we have to be careful here. Okay, so if I'm going back to my drawing, here's 1 degree, here's 60 pieces here, and then this 1 is built into 60 pieces, so it'd be 60, 60, 60, 60, all the way through 60 times. This one is divided by 60 over 60, okay, or 60 times 60, which is 3,600. Okay, so the seconds, we have to take 60 times 60. And the final answer for this one would be 13.2483 repeating with the degrees. Again, the whole idea is to get into the whole number degrees, and that's why we ended up having to divide by so much on that last piece. Okay, so let's use this to answer some questions. Okay, I told you this was dealing with longitude and latitude. Here's how it works. We can use a sector, what we were just doing, to determine the distance between 2 cities on the globe, as long as those cities fall along the same longitudinal line or along the same latitudinal line. Okay, if that's happening, this little piece here is a sector because it's marked by an arc from the core of the Earth. Okay, well, if it's a sector, then what we need to deal with is knowing the pieces needed for that. Okay, if it's distance, we're going to use circumference, and the pieces we need are the radius and that angle in between. Okay, so let's see a problem for this first one. Okay, it says Grand Rapids, Michigan is on a longitudinal line of 85.67 degrees west and a latitude of 42.97 degrees north. Louisville has a longitude of 85.77, and you'll notice these numbers are fairly close together. Then it's 38.25 degrees north. Because those longitudes are so close, we're going to assume that they're the same. We know they're not, but for our estimation, we're going to assume they're directly on the same line. Okay, so how that would look on my globe here, and I'm going to back it up just for a second. If they're on the same longitudinal line, I could say this is my Grand Rapids, Michigan, and here's my Louisville, Kentucky, and just draw one sector to deal with this problem. And that's what we're going to do on your work here. Okay, we're going to find the numbers that are close together and get rid of them, and we're only going to focus on the rest. So I want you to draw a sector for me. And at the top, you're going to label that point just like I was doing, Grand Rapids. And the second point is going to be Louisville. Now, if you know a little bit about geography, it's nice to have the one that's more north on the top and the one that's more south on the bottom, but it's going to work out the same either way. All right, and what we need to do is figure out this angle in between. Okay, this angle between is just the distance between those two numbers that they're given, because they're really both measured from 0. I just need the distance between them. We'll subtract them. So make yourself a little note of this. Theta is going to be your 42.97, the bigger number, minus the smaller number. Okay, and when we subtract those two things, we get 4.72 degrees. Okay, so we've got our theta. Okay, then it says we want to know if the radius of the Earth is about 3,960 miles, find the distance here. Okay, the distance is another way to say the length of that arc. So this is a circumference problem. 2 pi r is our formula, and then we're going to multiply by theta over something. Because this theta was in degrees, we're going to use 360. Okay? Now, because this is a problem that's going to ask us about the distance in miles, this is one where we don't have to do any reducing beforehand because we're not going to get the exact value anyway. We're just getting an approximation. So we'll end up typing the whole thing in our calculator, including that pi. So when we put this formula together, we're just going to smush it all. We won't worry about reducing, and we're throwing it all together. And that's exactly how we're going to put it in our calculator as well. Sorry, my decimal got off here. So in your calculator, all in one go, 2 pi 3960, and then times our 4.72 divided by 360 for a final answer of about 326 miles. That's it. Okay, we reviewed that decimal degrees because sometimes, like here, they don't give you the longitude and latitude in decimal degrees to start with. They give it to you in a more common measurement for navigation, and that's the minutes and seconds. Okay, so same process here. It says, let's assume Grand Rapids is also directly north of Montgomery. Okay, so they don't even give us the longitude numbers, they just give us the latitude numbers. So here is my Montgomery, or there's my Grand Rapids, excuse me. And there's my Montgomery. And I just need to find theta by subtracting these things. Okay, you can convert them first or subtract them first. I would recommend that if this number actually subtracts nicely without negatives involved, then I would want you to subtract first, then convert. Because sometimes, though, you have no choice but to convert first. Alright, so in this case, we can subtract straight down with no problems. This is 10 degrees. This 58 minus 22 is 36 minutes. We know we divide that by 60, and that's 10.6. Okay? If you wanted to convert them first, because like I said, sometimes you have to, I'm going to recommend you do all that work in your calculator. Here's how it would look. 42 plus 58 over 60. Find that number. Then you take your 32 plus 22 over 60, and then you subtract them. So first number minus second number. Sorry, I'm struggling here. And you'll get the same thing. Okay? So now that that's there, we're filling out our formula. 2 pi r times theta over 360 because it was degrees. 2 pi times our radius was 3960. And we decided that was 10.6 over 360. And you're going to throw that whole thing in your calculator. Okay, when you do, we're going to round to a whole number, which looks like 733 miles. That's it. Okay, there are a couple word problems on your homework that we didn't talk about, but we talked about all the math that you need to be able to find them. So if you have any questions while you're working through those, please come see me.